In partial fulfillment of the requirements for a Bachelor of Science degree, the Civil and Construction Engineering and Architectural and Construction Engineering students at the University of Arkansas Little Rock participate in a culminating senior design project. Over the course of 2 semesters, these students work in teams to produce design and construction documents for a specified structure. Weekly meetings with industry partners, including construction managers from CDI Contractors and structural engineers with Cromwell Architects and Engineers, provide students with a unique opportunity to present their work and receive valuable feedback from experienced and knowledgeable professionals. Additional guidance is provided by faculty members within the Department of Construction Management and Civil and Construction Engineering at UA Little Rock. In the following presentation, the 16 UA Little Rock Spring 2021 CVCE and ARCE seniors present a summary of their senior design project in their own words.
Welcome to the UALR Civil Engineering Senior Design Project. My name is Mason Brown. Starting things off, the UALR Civil Engineering students and I would like to thank our sponsors for all their time and help this past year. Thank you to CDI Contractors and Cromwell Engineering. I will now go over the project overview. The students were all separated into teams. These teams were decided by taking a survey to see what strengths we could bring to our team. This way, each team member brought a different skill set to their team. This was based off our own real-world experiences. Once we were separated into teams, our faculty and sponsors gave us specific buildings and locations. For the specific building, we were to calculate all structural factors and members, as well as a base estimate with a construction schedule. This is where our building type and location would have a huge impact because weather and pricing in the areas. After hand calculating the structural members and factors, we were to make a RAM and Revit model to see if the structure was sufficient enough for completion. Before we started the project, COVID hit in March, so we had to adapt to online classes, which also meant senior design. We would meet with our teams and sponsors via Zoom meetings. When it was time to present our latest work, we would meet at CDI with 2 people from each team. COVID was hard to adapt to, but we all worked together. Communication was definitely key in this project.
Thank you for that intro, Mason. My name is Errol Craig, and I'll be talking about the project outline. So some of the tools that we used for this project included RAM, which is a structural building design software. We also use Revit, which is a building information modeling software. It's often used by project architects. It's also used by structural engineers, and people like project contractors are even able to use it. We also use PlanSwift, which is a takeoff and project estimation software. And just about everything else came from free programs from Google, such as Google Drive, Google Docs, Google Sheets, Google Slides, Gmail, and even Google Chat. We met twice a month for intermediate and deliverable meetings. And what an intermediate meeting is essentially just an opportunity for us to correct our mistakes from previous deliverables and then present those corrections. And a deliverable meeting is just a presentation of topics that we were assigned for whichever current deliverable we happen to be on for that month. And if you'll look below, you can see a list of every deliverable that we've done this entire school year. So deliverable 1, we had to present design criteria and column layouts and provide our schematics for our roof and floor framing plans and our site work estimates and schedules. For deliverable 2, we had to present the recommended specification sections and substructure and superstructure estimates and schedules. For number 3, we had to present our roof and floor framing design and plans, our submittal schedule log, our RFI and responses log, and our vertical enclosure and roof estimates and schedules. For deliverable 4, we had to present our column and foundation design. We had to update our RFI and responses log and plans and interior construction estimates and schedules. And for deliverable 5, we had to present our lateral load or wind resisting system, provide our first draft for the RAM gravity model framing plans. We had to update our RFI and responses log once again and provide our first draft for the structural Revit model, and also provide our review of the concrete mix design submittal and the interior finishes and estimates and schedules. For deliverable 6, we had to present our lateral load or seismic resisting system, and we had to update our estimates and schedules to incorporate the alternate of each, and we had to provide an updated RFI and responses log. Deliverable 7 just consisted of us providing a DD level drawings presentation and our RAM lateral model and an updated copy of our RFI and responses log. Lastly, deliverable 8 just consisted of us presenting our cost estimate and construction schedules. All right, so moving forward, our initial project phases required us to review the given climate summary and design criteria, which provided us with essential information such as various loads, internal pressures, wind speeds, seismic design categories, and a multitude of other factors that must be considered when designing structures such as these. And so what we did was we reviewed the preliminary drawings that we were given, and that helped us develop our initial schematic designs of the roof and floor framing plans and the preliminary foundation system for our respective projects. And below you'll just see some of the things that we had to take into account when we were designing our buildings. This is actually from my team 2, for the hospital in Minnesota. This is a climate summary and a chart of the average high and low temperatures in Minnesota. So if you'll look here, this is just a continuation of some of the tasks that we had to keep up with for this project. This included things like RFIs and submittals. So what an RFI is, it's just an acronym for request for information. And so it was essentially a tool that we use to get clarification on certain aspects of our projects. So we might have needed to know how thick we needed to design a slab, or how the thickness changed depending on what floor we were on. We would have to submit an RFI for information like that. Next, we developed our base and eventually our alternate project estimates and schedules. We then provided our structural steel specifications and our calculations for the roof and floor structural steel sections and our structural columns and footings, which were adjusted as needed throughout the entire project. We then provided lateral framing and main wind force resisting system, or MWFRS, calculations, and designed our 3D RAM and Revit models, with our seismic force resisting system selection being last. And thank you.
Next, we're going to get into design criteria. This is based on the building itself and the risk category of where the building is. All these figures you're about to see are based on the ISBN, IBC, Chapter 16, and the ASCE 7. Right off the bat, you're going to notice the dead loads. Minnesota has a significantly higher dead load than the rest. It's based on the snow load and the wind exposure of where the building is. Missouri obviously ain't going to have a whole bunch of snow, so the dead load for the floor and roof isn't going to be as much. And you can see the snow load corresponds with where the building is and how much snow they're going to receive per year. And corresponding with the snow load is going to be the snow exposure factor. This is based on if the structure is sheltered or fully exposed, and none of these are sheltered, so they're going to have a 0.9. And depending on what's going on in the building is going to affect the floor live loads. So you're going to have a lot of movement going on in an elementary school and an office as opposed to a college classroom. Then the roof live load, everybody chose 20 PSF because that's the minimal requirement for the building. Next, we'll get into ultimate wind speed. Based on where the building is, it's going to depend on your wind speed. Florida is obviously going to have a very high one during hurricane season. Same for South Carolina. Minnesota's and Missouri are going to have a moderate speed based on snow and blizzard factors. The terrain exposure, everybody's going to have a Category C, very open terrain. The seismic important factor based on the risk category. Risk Category 1 not a very high occupancy, risk category 3 and 4. 3 being a high occupancy for the elementary school, so they're going to have a 1.5, and then Missouri being a hospital, that's going to be essential facilities, so they get the highest. And then lastly, we're getting into seismic design category, A through D. A being minimal ground shaking, B being moderate, C being moderate to severe, and D obviously being severe ground shaking due to earthquakes.
So now we're going to talk about beam design. For the beam design, what was required was to know the shear capacity and moment capacity of the beams. Moment inertia was also checked to prevent exceeding deflection limits. The maximum deflection limits were determined for the dead and live load combined by taking the length of the beam divided by 240, and for the live load divided the length of the beam divided by 360. These are the applied loads. Obviously, they range a bit, with Minnesota having the highest floor dead load of 175, with Missouri being the lowest floor dead load of 75. The live loads range from 80 to 50 or 50 to 80, actually rotating between the locations. These floor loads were different based off what the building is used for. Minnesota was a hospital, Missouri was an office building, so obviously those are going to vary greatly in the dead load, with hospitals having lots of heavy equipment and office buildings not having such heavy equipment. South Carolina and Florida. Florida was used for elementary school. South Carolina with college classrooms. Obviously they're going to be a little higher than just an office building. Lots more people. Furniture. Live loads vary greatly as well. For the roof loads, they range from 20 to 30 for both the dead and live loads. For the geographical locations, the snow loads very different. Obviously, you're not going to have snow in Florida, and rarely, if ever, in South Carolina. So Missouri and Minnesota really only have the applicable snow loads that would affect the design at all. And so for the beam design, we took those applied loads and we applied them to the schematic designs. And earlier in the design process, each group was told to design the building, do a rough layout. So they took bays and girders and beams and laid them out. Majority of us used the plans and just took a pen and drew over them. But these bays varied in sizes, so the girders were different for each group. The beams were different for each group. The lengths changed a bit. It really all depended on what that group felt best for their location. But these differences are going to affect the types of steel that we have. So the applied loads and schematic designs were used to come up with the moment capacity and the shear capacity. These numbers were taken to the AISC steel manual, where they were compared to the list of beams in the tables, and we chose the most economical steel member for our building, or each group did for their building. And these differences obviously show up in the finalized steel. So the deckings were the same for 3 different groups, just different in South Carolina. Joists were not calculated for in Minnesota and South Carolina, but in the spandrel beams, Minnesota had the heaviest, with Missouri being the lightest. Missouri was the lightest for the majority of the way through here, obviously because their loads were much smaller. And for the floor design, Minnesota was typically the heaviest, except for down in spandrel girders, where South Carolina had the heavier spandrel girders. And for the roof, here, surprisingly enough, Minnesota had the lighter girders for the roof. Decking was either B22 or B20 for these groups. But again, Minnesota had some of the lighter steel. South Carolina with the heavier steel in their girders as well. Typical beams were different in each group. Obviously, Minnesota and South Carolina didn't calculate for typical beams. They just used joists for the roof. And these were all the finalized steel members. They were run against a RAM model, which we'll discuss later, but the RAM model either confirmed or denied our suspicions for, or our calculations for our steel. If they did happen to vary, hand calculations were redone and retested with the RAM model until the lateral and gravity models passed and approved of our steel choices. But these were the final steel options.
Hi guys, I'm Mohammed and I'll be presenting the column designs part of our project today. Project. Column design basically depends on column loading, and that is based on dead and live loads, and dead and live loads could differ with the building used. In our case, we got 4 type of buildings. It's elementary school, hospital, offices, college classrooms. When talking about the axial loading, it includes floor, roof, and wall loads. And determination of column sizes depends on maximum loading that occurs in the column. And when doing column splice, it basically depends on the strength and the cross-sectional area of the steel. What is a column splice? The column splice is basically joining of 2 parts of column, so the forces and the moments could be transferred from one part to another. And we'll be using 2 terms in the last table probably. It's a top and bottom. So when we say top, it basically means section above splice, and when you say bottom, it says section below splice. And there is a picture of splice. So moving on to the tables, here we got the dead and live load table for floor, roof. So we got different numbers here for like this in Florida, for St. Louis, and each one of them have different numbers because it depends on the usage of building. So here we got a table that shows us interior, exterior, corner size of the column for top and bottom both. And at the bottom we got the size of splices, both bolted and welded.
Hi guys, my name is Caleb, and I will be covering the foundation design portion of our project. So when looking at foundation design, there are 2 main factors that we want to kind of consider. Soil bearing capacity is the first one, which in layman's terms is essentially the strength or the rigidity of the soil. So obviously the stronger your soil, the less area your foundation is going to have to be. And the second thing that we want to consider is the frost depth, which is simply the depth to which the groundwater in the soil is expected to freeze. So if we look over here to our right, we can see that the locations in the southern part of the United States, such as our Florida location and the South Carolina one, is going to have a much lower or much shallower frost depth than, say, the location in Minnesota. So when we look at these 2 factors and we compare our results, you can see that Minnesota, which has the strongest soil bearing capacity and the most deep frost depth, is going to have the smallest area when we look at our foundation size. And in conjunction with that, South Carolina, having the weakest soil and the most shallow frost depth, is going to have the largest area. Next, we will cover lateral wind design.
Hello, my name is Josue Castellanos, and today I'll be talking about lateral wind design. The lateral wind design was based on design criteria found on Deliverable 1. Chapter 27 and Chapter 28 from the ASCE 710 manual were also used to find other parameters. Building code required the building be classified by their level of importance in determining the risk taken, with safety factors against their failure under critical design loads. Risk Category 1 represents a low hazard to human life, while Risk Category 4 represents a high hazard to human life. The exposure factor is determined by the location of the building, and it ranges from B to D. With equation 28.3-1, we were able to calculate the wind pressure of the building. Then, we used table 28.2-1, which provided a step-by-step procedure to determine the wind load of the building. The wind load was distributed to the building envelope, and then we calculated the wind pressure on the surface of the building. With the calculated wind pressure, teams were able to calculate the wind story shear by multiplying the wind pressure times half of the height of the wall above the diaphragm plus half of the height of the wall below the diaphragm, leaving the force in pounds per linear foot. The force was distributed to the horizontal resisting members, and with the help of the Bulkcraft manual, teams were able to analyze if the diaphragm will have the shear capacity to carry the story shear load for each level. The actual wind load acting on the bracing was calculated by multiplying the shear force in each level times the length of the building. This load was applied to the bracing, and with the help of the method of sections, teams were able to design a brace frame using the AISC steel manual. Braced frames were designed for strength. Each team chose a different type of bracing solely for the aesthetic and functional purposes. And now, we will be talking about lateral seismic design.
Thank you, Josue, for introducing lateral design with your discussion of wind loadings. Hi, I'm Virginia Lance, and I'm responsible for the discussion of the seismic portion of the lateral design. I chose this topic because of a fascination with the movement of the Earth and geology in general. It's because of this interest that I am impressed with humanity's ability to create sustainable and long-lasting structures which are able to withstand the forces generated by the Earth. Between the wind and seismic lateral loadings, seismic actually drove the design for 3 out of 4 of the locations, and we'll take a look at why this is so. The axial seismic loading is determined by the computation of the base shear V, which is represented here in kips. Several factors are used to determine the base shear, among them the site class, the SDS factor, the seismic design category, the seismic importance factor, and the response modification coefficient, R. Of these factors, all but the importance factor are based on the movement of the Earth. The importance factor is solely based on the building use, which is defined by the risk category seen here. This USGS map shows the seismic regions of the United States based on the shaking intensity that is felt in the event of an earthquake. I have added stars to indicate the location of our 4 projects: Minneapolis, St. Louis, Destin, and Charleston. Interestingly, as we will discuss, it is the movement of the Earth that determines the base shear and not the risk category of the building. This chart shows the color coding of the map, which indicates the intensity of shaking that could potentially be felt in the corresponding regions. Minneapolis and Destin are in regions where shaking is the weakest, while St. Louis would experience severe shaking, and then Charleston would experience violent shaking. And now, comparing the previous map to our data, you can see that the wider range of values represented by those movement factors in comparison to the importance factors generates a much greater impact on the base shear than the importance factor does. For example, Charleston's college classroom is merely a risk category 2, yielding an importance factor of 1, which generates 0 effect on the value of the base shear, which is 915 kips, the strongest base shear, because it has the highest SDS value and the highest R value. And consequently, it would require the strongest lateral reinforcement. Conversely, the hospital in Minneapolis has a risk category 4, generating the highest importance factor of 1.5, yet it shows the lowest base shear of 190 kips due to its position in a low seismic activity region. Another interesting thing to note is that the elementary school in Destin and the college classroom in Charleston are both coastal cities and both may experience hurricanes. Yet Charleston's design is driven by the seismic portion of the lateral computation instead of the wind because of its seismic location. A hurricane cannot even compete with the movement that Charleston may experience in the event of an earthquake. I think that gives us an idea of how powerful the earth is. Determining which section of the code that the building needed to comply with was one of the greatest challenges of this project. As you can see, section 11.4 referred us to section 11.7, which in turn referred us to section 1.4. The code is quite thorough with respect to attempting to address as many different scenarios as possible, but this also makes it a very time-consuming document to track through. This is one of the factors that made this project a taste of the real-world application of all that we have learned. It was an extremely educational experience, and I'm very thankful for the opportunity. Next up, Mohammed will discuss specs, submittals, and RFIs. Thanks.
This is Mohammed Ratibi. I will talk about specs, submittal, and request for information. Specification. We were tasked with going through the CSI master formatting and choosing all of the subdivisions using our building. Submittal log. We were given the task of filling out a submitting log. It's a document created as a tracking mechanism to ensure that the designing team approve all the materials and the final design before installing this task. We were given a different specifications section. Each group was responsible for cataloging the information including in each area and then determining the appropriate data needed to be submitted and reviewed by all involved parties. Submittal review. The team was given a concrete specifications as a different concrete protecting sheet for potential protect. We were asked to go through both and set if the protected data meet the specs requirement. This was then logged in the submitter review log. Requesting for information. The summary log. Each team keep a detailed log of their request for information to help keeping track if don't resolve the questions has been answered on the time. Next, we will talk about base estimated.
Hello, my name is Justin Mitchell, and I'm going to be covering the base estimate. The base estimate is the entire estimate except for the alternate third floor estimate that will be covered on a later slide by Jesus. For this estimate, all four teams estimated the same overall building layout. Each team had different locations, which changed the pricing for each item as well as the structural requirements. For the estimation categories, we received a template from the industry sponsors at CDI. They had different categories like general requirements, which included things like temporary facilities, which would include all job trailers, admin, which would be all personnel costs for staffing the project, equipment rental, had site work, which would include earthwork, utilities, landscape and irrigation. It had building, structure and shell, which would include concrete, metals, and mechanical and electrical costs. It had interior finish, which would include woods and plastics and your doors and windows, and fees, which would include contingency and bonds. For the different takeoff software you use, each group used different kinds of softwares with what they felt comfortable using. We used AutoCAD Civil 3D, On-Screen Takeoff, and PlanSwift. And for the cost estimation software used, we all basically used the same software, which would be RS Means Estimation Software by Gordian, as well as industry-sponsored guidance and prior knowledge gained from internships. For the group comparison, we had two groups that were around 12.2 million and two groups that were around 13 million. These differences can be attributed to RS means adjustment factors for individual areas of the country. This takes into account the price for different materials for each city and adjusts the pricing accordingly. We had different design considerations, things like different sizing requirements and different designs, things like snow loads and seismic. We had different software that was used, rounding up or down, experience levels, and varying level of conservativeness.
Hello everyone, my name is Jesus Martinez, and we're going to be talking about the alternate estimate for the senior design project for the class of 2021 at UALR. So as Justin previously talked about the takeoff process and the software, the quantification that goes into it, we're going to be adding a little bit to that in this alternate. So the alternate entails completing the interior finish out for the north half of the third floor. And we're going to look at the third floor plan and reflected ceiling plan here in the next slide to see what all is going to be added. So the scope of work that we're going to be looking at is actually woods and plastics, doors and windows, finishes, miscellaneous specialties, furnishings, and mechanical, electrical, and plumbing systems. So let's look at the alternate third floor plan and the alternate third floor reflected ceiling plan, and then we'll look at all the team results. So here on the left side we have the original third floor plan that was provided to us by the sponsors. We can see the north upper half of the building is pretty empty, it's just shell space. We can see to the right in the upper half we have new rooms, new offices, new restrooms, and to the right of that we can see the legend for what those colors mean, and we can see that new tile is going to be added, new carpet, porcelain, rubber base, and of course sheetrock and all of those things. To the bottom of that we have the alternate reflected ceiling plan. So we can see that new acoustical ceiling and new gypsum board ceiling is going to go in to a couple of those areas where we didn't have anything before. So we can see that example of the plans of takeoff there. So now let's move on to team results. And here we can see all the team results, their location, and kind of a price breakdown of what everybody came out with for general requirements, the interior build out, which was the main thing, and of course fees, which included contingency, insurance, and bonds. And of course, as Justin mentioned before, disparities are going to come in with pricing based on location. Just quantities might differ between teams, and just sometimes maybe the price isn't as broken out as we needed it to be. But overall, we see that all teams were in the 2 million range, and the highest was in the 3 million range. So now we're going to have Jeffrey talk to us about the base schedule. Thank you, guys.
Hello, my name is Jeffrey Snorman, and the next thing we're going to look at is the schedule, our base schedule. So the schedule, we use the estimate for the most part to help design our schedule, and then after that we look at a lot of different things that went into making the schedule. So one thing that went into it was, of course, where groups were located, different weather conditions, and different things you have to look at in that area. The project we used in order to make our schedules was Microsoft Project, which allowed us to put different things in as we came across them and link them together into a Gantt chart so we could figure out what activities could be going on at the same time and what couldn't, so we could link them in order to figure out the overall duration of our schedule. And like I said, different things were impacted based on where you were. And so through Microsoft Project, we were able to make charts and kind of build a base schedule. And then we got to our results, and as you can see here, every group was around 12 to 13 months. And like I said, locations impacted a lot of what areas you could start and finish. Like the Destin, Florida group had to consider hurricane season and things like that for when they were starting and when they wanted to be doing work outside versus inside. Minnesota had to consider more of winter periods for, they didn't want to be doing work outside, during the winter, so you had to wait and start a little bit later so you could have most of that done and be working interior work as you get into the winter. And then, South Carolina had to deal a little bit more with your rains and hurricanes and things like that. Missouri didn't really have to deal as much with weather conditions. And so when it all came out, this is about what we all got, was around 12 to 13 months total.
Hi, this is Chris Reyna. I'm presenting the alternate schedule for the project. So the alternate schedule was for a project at the hand. We were tasked with providing an alternate estimate for the interior of the third floor. This alternate estimate would need a time frame for the owners, and so because of that, we created an alternate schedule to configure how long the duration would be, or if it would extend the project in duration, or if it would decrease it. So the software that we used to figure this out basically was Microsoft Project. And so the next thing is the screenshots, basically the final touches of what each team provided. So here's the screenshots for Charleston, South Carolina, Team 4. This is their alternate schedule that is going hand in hand with their estimate. This is a screenshot for St. Louis, Missouri, team number 3, and there's their duration. Here's a screenshot for Minneapolis, Minnesota, team number 2, and their alternate schedule. And the last team screenshots for Destin, Florida, team number 1. And so the reason why we were presenting this is because of the fact that the duration were very, very similar, and basically adding on the alternate to the project, there would be 1 month that would be added to the duration of the project, and this alternate schedule really focused on this interior finishes that are part of the alternate estimate, and basically this changes other durations that might have a lag into becoming 0 extra days, meaning that other tasks that can be completed in maybe a certain amount of days and still have extra days in case there is something that comes up. They would become primary tasks that need to be completed then and there. And so the alternate can be accomplished hands down. We just need to schedule it accordingly.
Hello, my name is Jonathan Gentry, and I'll be talking to you about how we students used RAM structural system to model our gravity and lateral models. So first off, what is RAM structural system? RAM structural system is a structural analysis software that is made by Bentley for structural engineers in order to streamline the overall design process. It is a program with a simple interface that is fairly easy to learn the basics of, but there is a lot of behind-the-scenes stuff that someone running the program must be aware of in order to get the results that are both accurate and make sense for the project. Once you learn the program, it allows engineers to be much more efficient with their time, as it is much quicker than doing hundreds or thousands of manual hand calculations that would otherwise be required to figure out the different member sizes for a large project. Some of the things that RAM allows users to do is easily input their building geometry and different load data, perform analyses to get appropriate member sizes, and make sure that they adhere to local building codes, as well as export the results into a PDF form that is easy for transmittal or printing purposes. As far as the overall design process goes, we were all heavily encouraged to perform our hand calculations first and really understand how we got to those results. This allowed us to have an expectation of what the results from RAM should look like. For the most part, the results that we got from RAM matched our hand calculator results and overall made sense. Now, whenever the results differed greatly, it was usually due to us not understanding a certain aspect of the program. And this is where help from our industry sponsors came in handy. Whenever we would get an error, it was almost always a simple fix of just changing a variable or a value that you might not think of when doing hand calculations. Now, for instance, this error shown here was brought on because we did not realize that RAM required the users to manually input member sizes for its brace frame analysis, because for most other members, it calculates the required member size based on the loading that you input into the model. So as you can see, understanding the RAM software is very important in order to be able to achieve good results. Now, while you are able to modify the color scheme if you wish, the default color scheme within RAM is as follows: yellow for all foundation and footing members, cyan for gravity members, red for lateral members, and purple for braced frame members. Also shown in this screenshot are the different floor decking levels, as well as the direction of the span of that decking, which is shown by the small purple arrow lines. The code check is basically the ending step that we were tasked with completing within RAM. After you figure out all of the different member sizes and input them into RAM, or use the sizes that RAM itself assigns, you are able to run a lateral code check. This uses whatever building codes that you tell it to, and it checks all of the lateral framing members against that code. The results of this code check will basically tell you how much of the overall member capacity is being utilized. It goes on a color scale from dark blue all the way to red, with red indicating that the member has failed. In this case, the user is able to change the assigned member size and rerun the analysis until that member passes. Now, after all of the members are shown to be passing, we then used all of the member sizes from RAM to build our Revit models that we then used to make up our design and development drawing sets.
Hello, my name is Cami Lambert and I'm going to present to you the drawings and details from our project. We were tasked with developing our drawings and details in Autodesk software Revit. We had to develop a complete set of drawings consisting of general note sheet, foundation plan, floor framing plan, roof framing plan, brace frame elevations plan, and typical details. In this first sheet we have here is the general note sheet. This sheet contains the summary of our general specifications, which vary for each group. The next sheet is our foundation plan. From our foundation plan, you can tell what kind of footing type we use, which was continuous footing. You can also locate the columns used and their sizing. In the bottom left-hand corner of this sheet, you can find a structural foundation schedule to help locate all the components within the drawing. Here we have the floor framing plan. The floor framing design is different for every group, but most of our floors were designed the same, some designed differently for the different load paths we each had. The beams and girders can be found on this sheet, as well as the decking, where their sizing and locations are displayed. On the bottom right and left sides of the drawing, you can find where the stair openings and elevator shafts are located. Now we have the roof framing plan that displays our roof framing designs. Again, like the floor framing plan, the beams and girders can be found here, as well as the decking, where their sizing and locations are displayed. Here we have our braced frame elevations. For the bracing design, each group had different designs based on the different design criteria we were given. The braced frame elevations that are shown on this sheet are from Group 1, who used double diagonal bracing, also known as X bracing. All the other groups use K bracing, also known as inverted V bracing. In the last sheet we have here, you can find the typical details. There is a detail for interior and exterior footings and columns, a detail of the continuous strip footings, joist and girder conditions for a typical roof and typical floor, and beam and girder conditions for a typical roof and typical floor. That was our complete drawing set and details, and I'll now hand it over to Jasmine to wrap things up.
Hello, my name is Jasmine Ball, and I will be presenting the closing statement. As some review, there were 2 phases we had to go through to complete our project, and each phase contained 2 deliverables. In deliverable 1, we were to develop design criteria, column layout and framing plans, and develop a site work estimate and schedule. In deliverable 2, we were to select structural specifications and develop a substructure and superstructure estimate and schedule. In phase 2, we had deliverable 3 and 4, in which we were to design typical roof and framing conditions, develop RFIs and submittal schedules, and develop exterior vertical enclosures and roofing estimate and schedule. In deliverable 4, we were to design columns and footings and develop interior estimate and schedule. Phase 3 contains deliverable 5 and deliverable 6, in which we were to design lateral load resisting system components for wind and develop a RAM and Revit model. We were to review the concrete mix design submittal and develop an interior estimate and schedule. For deliverable 6, we were to continue to work on our RAM and Revit models, while also incorporating the alternate information for our estimate and schedule. In phase 4, we had deliverable 7 and deliverable 8. In deliverable 7, we were to design lateral load resisting system components for seismic, develop mechanical, plumbing, and electrical estimate and schedule, develop a general conditions and general requirements estimate, and develop a lateral RAM model. In our final deliverable, we were to complete drawings. We were to finalize all prices on estimate and durations on schedule, review clarifications, and update foundations and superstructure estimate per final design. Our total work hours were 1959.5 hours. There were some different outcomes, mainly from the structural side rather than the estimating side, but those changes were still minute. Estimating changes came from things such as frost depth or adding in a location adjustment factor. But even with these different factors, the final estimate and calculations were within a close range. As a team, we had to learn not to procrastinate, stay on schedule, and follow the calendar. It is important to you and to everyone to work together so we can provide the best outcome for our projects. We were also lucky enough to receive real-world experiences that will help us in our future. When we first started our projects, we were unsure we were doing the right things because it was so new, and we had to learn how to trust ourselves and our knowledge, and over time we started gaining confidence and putting our teachings to the test. There were many hurdles, especially in a team-based environment, that we had to overcome. We had to adapt fast to the new changes. We would have to incorporate new drawings every week and new information, and we had to act fast on that. We would like to thank the industry sponsors and faculty for guiding us through this project with patience, understanding, and a real-world knowledge that will help us grow as individuals within our degree field. We would also like to thank the Arkansas Society of Professional Engineers for being here and listening to us and having an interest in our future. Thank you.